Good afternoon, everyone. I'm Shunan from Chicago. Welcome to Action Distinguished Lecture Series. Today's webinar focuses on retrospective insights into adversarial machine learning from Professor Patrick McDaniel. A little bit background of Action AI Institute. It is led by Professor Giovanni Vigna. It unites 11 universities across the US. Each quarter, we host a distinguished guest speaker who was voted by us in the Student Advisory Council and specializes in the intersection of security and AI. So as we proceed, please feel free to submit your questions in the chat window and we'll record it. And in the end, we'll have like a 5-minute, 10-minute Q&A session, depending on how we go. And then, Professor McDaniel will answer as many as time permits. So we'll record this presentation as well. So you can check back later on our YouTube channel. So today we invited a technical giant, Professor Patrick McDaniel. He is Tsun-Ming Shih, Professor of Computer Sciences in School of Computer Data and Information Sciences at Wisconsin-Madison. And Professor McDaniel is a fellow of IEEE, ACM, and AAAS. And he is also the recipient of SIGOps Hall of Fame Award and ZigZag Outstanding Innovation Award. And also, like he was the director of NSF Frontier Center for Trustworthy Machine Learning. So Professor McDaniel's research focuses on a wide range of topics in computer and network security, as well as technical public policy. So without further ado, I'm honored to welcome Professor McDaniel to our virtual stage, and please take it away. Yeah.
Excellent. Well, thank you so much for that gracious introduction. And thank you for inviting me, and in particular, Giovanni, thank you for the invitation, as well as the folks there at Action AI. So what I want to do something today is a little bit different. What I want to do is I want to try to capture a moment in time. We're actually a decade in time. We're about a decade into this revolution around AI. And our understanding of security in that world has sort of evolved. And I want to start at the beginning by setting some baseline understanding, talk about what is security and talk about what is AI and specifically machine learning, and then talk about some of the vulnerabilities that we've discovered over the years. And then maybe spend a fair bit of time really sort of discussing what are sort of some key insights about why AI is vulnerable. And then I want to end and I want to talk about us, not simply as a technical community, not simply as people that are involved in large-scale research, but as a society and as a species, we have to understand what are the implications of AI and machine learning. And so maybe I will start at the societal level, and that is we're in the midst of perhaps the biggest societal change within the last 250 or 300 years. Really, it's the Industrial Revolution is the only thing we can possibly compare to what we're in the middle of. And we're at the very, very nascent stages of understanding AI. AI, I think it's fair to say, is simply going to change the nature of existence on this planet. And I'll give you an example. So this set of trucks are doing what's called platooning. And I was actually in Germany with my wife and kids, and we were on the Autobahn, and I saw this line of trucks come by. And the first truck, there was a driver, and the trucks behind them, there were drivers who didn't appear to be doing anything, but they were driving about 2 or 3 feet behind the front truck. And in that moment, I began to understand, oh, wait a minute, this is what's called platooning. So the first truck is driven by a human being, and the remaining trucks were driven by AI. Now, this was 4 years ago, before COVID. So this was, again, the very early days of autonomous driving. But it was sort of a moment in which I saw the world change. Now, I come from a small county, the 8th poorest county in the United States, a little county on the Ohio River across from West Virginia. And It's it's flyover country. The biggest industry, apart from a university that's in the county, is actually transportation. They have trucks rolling through this little town called Athens, Ohio, where they're transiting goods. And a fair number of people that are involved in the trucking industry are dependent on these trucks that are driving through Athens. And so the trucks are going to continue to drive through Athens, but the people will be missing in the future. And so what this is going to do to a small county like Athens County is that it's not only going to take away the people that are working on trucks and driving trucks, but the secondary people, the people that are supporting, for example, the restaurants that are frequented by the people driving these trucks, and the handlers inside of factories that load and unload these trucks. And so what we're seeing and what we'll see in a place like Athens County is the very fundamental financial structures will have to change in the next 15 years. And I use this as an exemplar, not to simply just say that AI is really important, it's going to harm these small counties, but it's going to happen in every single sector of life, including living in universities. There are many things that we're learning very quickly that AI can be more effective and more efficient and frankly cheaper than the human operation of universities. And the same is true of financial industries and healthcare and pretty much every other endeavor of life. And so what this is going to lead to is social disruption. We saw this at the end of the Industrial Revolution, or during the Industrial Revolution. Society just simply had to adapt. Cities became the centerpieces for humans. Rural counties or rural areas became much less populated. There were far fewer people involved and it changed the nature of society. It changed the nature of the skill sets that were required. And so as we move into this world, we have to think as not simply this as a new technology or what new cool app does AI actually enable. We have to ask ourselves, how is this going to change society? And this is really important with respect to the human scale of just general employment. Many jobs, something like perhaps half or more jobs in the United States will disappear over the next 15 years. And that's going to require us to change how we do things. But at the same time, we have to start asking ourselves, well, as we go through this unavoidable transition as a society to moving many of the tasks and many of the jobs into an AI sphere, we have to begin to ask the fundamental questions about security and safety. And so just as a side note, in these lecture slides, I'll provide these at the end of the lecture. At the bottom are these blue boxes are particular papers. If you're interested in the topic that I'm talking about at that moment, those blue boxes will tell you where to look. And they're all available on my website. So coming back to the safety and security question, as we move, as entire societies move, we have to ask how this new technology will be abused by the adversary and how that technology can be used against us. And of course, we know in the security community, the answer to both of those questions is always yes. We just have to figure out what that means. And what makes it so challenging today as the cognoscenti, the people on the very front edge of AI and security, is we don't even agree on what secure means in this space. And I'm really going to bring that point home in a little while. But before I get there, I want to talk about machine learning. And when I talk about machine learning, I'm also talking very generally about AI, but I'm going to focus on machine learning. But most, if not all of the things I'm going to talk about really apply broadly to AI as a construct. So this is probably, for this community, probably not worth spending a whole lot of time in. How ML works, you got a bunch of data, you've got a learning algorithm, and that learning algorithm creates a mathematical structure called a model that is representative of some underlying phenomenon. And then you use that model at inference time. You're going to use that AI, if you will, to do something simple. I show an example of a classification problem here where we're taking a handwritten digit from something that's called from MNIST data set. And what we're going to do is we're going to give it to the model, and the model is going to tell us what that thing is. For example, this is just a general classification problem. So one thing we have to remember is AI in and upon itself has no intrinsic value. AI is simply a new widget to take things for which generally we do not have a closed form for, and have an approximation of what you would expect for a closed form. For example, in autonomous vehicles, such as I spoke about before, you have an autonomous vehicle that's driving on the road. It's constantly taking pictures. It recognizes through some sort of shape recognition that there's a sign on the road, and it's going to give an image, the pixels, literally the pixels, to a machine learning system. And that machine learning system is going to determine it's a stop sign based on us having trained that model over many stop signs in reality today for many years. And the key thing to note is these can be incredibly accurate, but what we know is that they are statistically accurate. They will be wrong some of the time. And that's what's key, is that if you have a system that can be wrong, we know in security that finding where it's wrong and then for an adversary inducing it to be wrong is where vulnerability lies. So let me just talk a little bit, again, for this community, it's probably this is all probably very basic for you guys. We're gonna talk about machine learning, but the first thing I want to acknowledge is that it's not magic. So here's our data set. We're gonna do what the internet does well: kittens and puppies. And what we're gonna say to ourselves is that we're gonna train a kitten and puppy detector. And so this kitten and puppy detector is given these particular values. Now, forget everything you know about kittens and puppies. Assume this is everything you know about kittens and puppies. And I will tell you that, I don't know if my cursor is working, this, and this are cats. The rest are dogs. So the way this would work in machine learning, obviously, is you're going to take features. We're going to take ears and tails, whether they're shorter or longer, or pointy or floppy. And we're going to take that information. We're going to encode each sample. And then what we're going to do is we're going to plot this in this two-dimensional space, not a high-dimensional space yet. And what we're going to see is the cats are clustered according to those features in some dimension, and the dogs are clustered in another. And therefore, that's how it works. All you need is an exemplar of the different classes of the phenomenon that you want to characterize, and you have a working machine learning system. So fantastic. What happens is now we have a model, we put it in practice, it's inside our car or for whatever our application is for detecting kittens or puppies. Now we give it a real sample, and that sample, we give it to the model, and it says, okay, you've got a long tail, you got pointy ears. Okay, bam, it's a cat. It lays right within our decision boundary, and we have an accurate cat detector. And so this can be a little comforting because if you become really good at this, it feels like you have a system that is a really accurate detector. And it may be an accurate detector, but that does not make it an accurate detector in the presence of an adversary. So the question is, what if we give it something like this, right? So this is neither cat nor dog, and this is what's referred to as an out of distribution sample. And this sample itself, we don't know where it's going to land. I suspect that it would look at something like the tentacles, and it would say, okay, those tentacles look like tails, so it's probably a cat. But the point being is that your model is only as good as the data that you actually give it. And that the implication of that is your model is only as secure as the representativeness of the data you use to train your model. But there are bigger problems here. Take, for example, the thing on the top right. So I show you again my training data, and the thing on the top right would be classified as a cat. And you might ask yourself, Why is that? Well, it would be classified as a cat because it's white. So in this case, the model itself, if we didn't just bind ourselves to the tails and the ears, the cat would be one feature. The color of the animal in the picture would be a feature. And if we blindly trained the model, we would simply say that all cats are white. This is called false learning. And this happens all of the time. You have implicitly bias. And as it turns out, this is one of the big problems. So bias can lead to insecurity as well. If I understand the bias of a model, I can exploit that to my own end. The one in the bottom right is actually a dog. Now, this is a little less obvious why this is. And that is because it has green on it. If you look at all of the images that we've trained our model on, the only ones that have any green on them are dogs. And this is another example of bias, but here the bias is using features that are not related in any way to the phenomenon we're trying to measure. And it turns out this is another big problem because we can exploit useless features in a trained model, particularly useless features that we can control to change the output of the model, whereas the underlying thing, the underlying phenomenon, isn't actually changing. Now, there are other things that we want to think about when we're talking about the security of machine learning, and one is that it has incredible capability. Some work that happened in the mid-teens created generative adversarial networks, and essentially this is a way of exploiting the data that's in a model to create some output that is representative of that distribution. And while that seems innocuous in practice, as it turns out, it's incredibly powerful. These three people on the left never existed. They look absolutely real. If I showed you these photographs out of context, you would say these people are real people. But these actually were generated. This is a website called thispersondoesnotexist.com, which is really fun. These examples are realistic. The text on the right, this is actually out of the University of Chicago, actually. This paper on the right actually demonstrates that we can do this with language, we can do this with images, we can do this with videos. And what all of this means is we now have synthetic reality. And we've seen things like revenge porn, we've seen things, deep fakes. We saw a lot around the elections of basically false reality being created. And this poses an existential problem for us as a society. How are we actually going to deal with this? So let me begin the next part by asking a question. How can it be used against us? So this is actually from a paper that my student Nicholas Popino and I wrote some years ago. The thing on the left is a stop sign. The thing on the right is a yield sign. And the reason it's a yield sign is because that image has been manipulated to confuse our image detection system. So both of this classification I gave you, stop and yield, were the result of, at the time, the best-in-class image recognition system. And what we found was that you could simply modify the image to get whatever outputs you wanted. And there's been a couple of parallel thrusts in the adversarial machine learning. Again, you folks are probably very familiar with all of this work that really represent two different kind of threat models. And I want to highlight the difference between the two basic threat models in adversarial machine learning and how they lead to, from a systemic standpoint, very different styles of attacks. But the first thing to note is adversarial samples are not new. Adversarial samples have been around forever. And an adversarial sample is simply just an input given to an algorithm that induces the worst case behavior. I used to work at a place called Bell Labs. It was called AT&T Research when I left in 2004. And this thing on the right is representative of something we were facing. So at the time, AT&T was one of the biggest ISPs in the country. And one of the biggest expenses, excuse, caught a bit of a cold over this last week, so you have to forgive me. So the thing on the right is actually spam, and one of the big expenses for AT&T was processing an absolutely massive amount of email, a lot of it actually being spam. And so me and a bunch of the other folks in the security group there were called in to try to figure out how the adversaries were getting so good at bypassing spam filters. And so what we found is that we found that certain user accounts would be compromised by an adversary. Some grandmother in Kansas would have her account compromised, and the adversary would send a spam email to her account and see if it got through. And if not, then they knew they had to modify it. Now, one of the quirks of the spam filter we were using at the time, I believe it was a variant of something called Spam Assassin at the time. It put it in your trash folder and then gave it a score. And that score, is really just a gradient. And so what they would do is the adversary would change the email, and then they would send it again, look at the score. Is it less spammy or more spammy? And if it was less spammy, they'd keep the change. And if it were, if it were more spammy, they wouldn't. And they would do this adaptively. And they'd do it over a period of time. And they would send enough email that eventually they would bypass the spam filter. This is known as an adaptive attack. Guess what? This is what we're doing in adversarial machine learning. We're basically creating adversarial samples by taking small incremental modifications and changing our output sample, and then looking at the result. If it gets better, and sometimes we can just calculate the gradient, so we always know it's going to get better with each perturbation. When we cross a decision boundary, then we have an adversarial sample. But again, this is just an example of finding the worst case behavior, the smallest set of changes we can get in order to induce a particular result. So the attack that we first worked on was basically back in 2016, was sort of an example of this. And I won't get too much into the details, but there was a attack about an L0 attack by Carlene Wagner, which did a kind of similar trick. That was also this kind of L0 attack. But essentially what happens is you start with your you start with your sample, you do something called the direction and sensitivity estimation, which is really just a way of figuring out what makes a 1 to the model, what makes a 4. And then you would simply look at all of the features and you would say, okay, this feature is most important to a 4, and you would simply flip it. And then you would check to see if the model now thought it was a 4. And then you would just keep doing that each time. And eventually, after you've flipped enough features, it turns out that the model would then think it was actually a 4. Now, if you remember our stop signs, they were a lot less obvious. We were doing this in MNIST because the perturbations are really obvious to change things from off to on, to give you a sense of the change. And it turns out there's something like 2 or 3% change in features for the MNIST data sets, and some later data sets was actually sufficient. But the idea is you're just incrementally changing. And it doesn't really matter. You can always start with any input and get any output. And you can either, on the left, you're adding, you're turning features on, and the right, you're turning features off, but you always get the same result. But what we learned at that point was, sometimes it's easy to create an adversarial, sometimes it's hard. And then if you want to think about this, really all we're talking about is modeling this phenomenon in some high dimensional space. And so what that means is some classes are further away from each other, and therefore you have to perturb them longer. You have to change it to get closer to the targets you're actually looking for. But the important part is you could always do it if you're willing to do enough work. Now, note, this has nothing to do with images. Although a lot of the early papers were images, it has nothing to do. This is a function of machine learning, of statistical machine learning. It's not, nor is it about deep learning or any particular technique. It's about the way we actually use the optimization and create the model. And it really doesn't matter what the domain is or the learning technique is. Now, there's a second strategy, which the original came out in 2015. Goodfellow and Segedi and Schlanz had the FGSM, which is really the first attack. And what they were doing is they were adjusting the input, but rather than pick individual features and have sort of drastic changes, they were able to change all of the features and do a very subtle overlay. And we refer to this as an overlay attack in order to get the adversarial result that you were actually looking for. And this was incredibly effective. And the way to think about the adversarial machine learning is there are really these two strategies. All of the algorithms in existence essentially boil down to one of these two strategies. You either have some sort of overlay in which you're controlling all of the features, or you have a saliency in which you're picking individual features and you're perturbing them. Now, this leads to some very different kinds of threat models. So again, if we're thinking about how they're being used in systems, if we're thinking about in a car, in order to use an overlay attack on a stop sign, you have to be able to perturb every single input, that is every single pixel, in that image of the stop sign and feed that through the system. So if you're inside the car and you're between the camera sensor and the model, you can do that. Whereas if you were outside the car, you need something that's a little bit blunter, like a saliency attack. And we've seen this sort of carry forward in the years that followed. If you remember the adversarial patches, when people were putting stickers on stop signs so that they could attack a certain part of the model with some very focused number of features. And those sorts of attacks sort of fall into the saliency category. But the fundamental difference I want to lay out here is they're very different threat models. And overlay kinds of attacks require the adversary to have very fine-tuned control over the input that the model is given. And where they have that control, they can be extremely effective. And with respect to things like human perception, if they have that kind of control and the changes are so small, they'll be imperceptible. However, if you don't have control, that level of control, say you're doing something like trying to bypass an intrusion detection system and you can only control things like header pit, sequence numbers and header fields and things like that, you don't have that kind of very fine-tuned control, so you have to use a more blunt instrument. And so as organizations like Action AI think about security, it's really important to really separate those kinds of attacks on systems because they really represent two very different kinds of adversaries and two very different kinds of adversarial assumptions. So when we're doing threat modeling, we really need to have a clear definition of what that adversary is, what its capabilities are, and what degree of control do they have over the input feature space in order to really understand what are realistic attacks. So just to highlight some of the results we've had over the last few years, we began to ask ourselves some important questions about how do we actually start defending these models. And so one of the things that I had thought from the very first days that I got into this space was that most of the modeling of the adversary did not take into account that they were dealing with a real input phenomenon. And what I mean by that is when you create an adversarial sample, there will be samples that are not realizable in reality. So I'll give you I'll talk about that in the image space first. So if you have an image that's taken out of the front of the car, we know because of the diffusion of light physics, you will not see massive differences of light intensity on pixels that are next to each other, simply because the way light diffuses. And so if you run something like an overlay attack in a naive way, it can generate images that look real to you or I, but if you actually looked at the low-level pixel-to-pixel light physics, you could immediately know it's adversarial because it doesn't obey the fundamental rules of light physics. Same is true. This is actually a study of network intrusion detection system, where most of the samples that when we ran things like even saliency attacks and overlay attacks in the network intrusion detection space, the samples were actually generating things that were not realizable. You could have things like round trip times going negative, for example, which obviously couldn't happen. And so we did a long study that actually began to ask the question of, are we vastly overestimating the power of the adversary because we're not paying attention to the fact that the things that are being introduced to these models are not really real, that they're sort of manifestly fraudulent, and we can identify them even before they hand them off to the model as not being real. And so that work went on for a couple of years, and really what we found was, yes, for most of the out of the box algorithms, they were actually generating a large number of invalid input samples. But on later work, we showed that we could modify the existing adversarial samples to basically do a second stage. We do the first stage to generate the sample, and then we would find some place and pull the sample back. We'd sort of correct the features. So it was like by adding a second optimization, you could basically make it compliant with the domain constraints. Second work that Ian and Dan and Nicholas we did a couple of years ago began to look at, okay, how many adversarial samples really are there? And so this paper, we really refer to this as an adversarial cone. But what we found was for most images that, and I forget exactly what this, and I'm blanking on the name of this data set. It's a very famous data set, but 60% of the images in this data set had adversarial samples in at least excuse me. Sorry, at least 20 dimensions. And so it turns out that in the space of adversarial samples, pretty much any sample you have, you can go in multiple directions. And so what that means is there's a lot of them. Something that's coming out right now is that in particular when it comes to something like images, we have discovered that that models are very finely tuned to texture. And what we found is that the way that most models are making their decision is based on repetitive low-level structures. And the implication for security is that there's whole classes of attacks which I can take if I can understand what the repetitive low-level structure that the model is concentrating on, rather than we think it's looking at a bike. Well, actually what it's looking at is correlations between the bike and for example, the pattern, the tire tread pattern. If I can figure that out, if I know what my structure is, then I can overlay that into my attack, and I can just pick a texture or a low-level structure. We call it texture because that's the name. That's what it's called in the image space. And we can use those textures to potentially be extremely powerful attacks. And in fact, when we went so far as to show, if you know about natural adversarial samples, things which models are just wrong about, we discovered that the vast majority of natural adversarial samples are the result of low-level structures. this goes beyond images because low-level structures are low-level structures. There's nothing magic about images. It's just repetitive structures within data. And so if we can understand for our target domain, what are those low-level structures, then we have an ability to either understand the adversary or generate very devastating attacks that may be very difficult to detect. So this is work that's ongoing. We just submitted it. The ink is still drying. We submitted it the last month. We suspect that there's some pretty profound results there that perhaps on another day, perhaps hopefully this summer, I'll talk more about it. So one question we have is, what does it even mean to be secure? So there's been a lot of work, and I suspect some people on this call have worked on model robustness. And the definition that many people accept is a model is robust with respect to a particular a point in the input space, if there are no adversarial samples within some sort of security bound sphere around that node. And so that's fantastic. It's a definition. There's been some really profound formal results. But from a practical standpoint, as a practitioner, as a fundamentally a security person, system security person, that is of intellectual interest, but it is very difficult for me to understand how such a definition is going to be useful in practice. How am I going to put that inside, say, an automotive system and say anything really meaningful about what the overall security of that system is? And so there's this war going on. And I remember Ian was talking about he never intended the norms to be a definition of security in the first place. But it's sort of been adopted for the lack of any other. And so I think one of the existential things we need to do in this community is we really need to get better definitions, better metrics for security. And particularly given the complexity of the things like DNNs, but and then even large language models, which are sort of unreasonable to reason about, we have to find some better definitions. So I'll just kind of briefly go. One of the other implications of machine learning is they just bleed information about their data. And the black box attacks, which we developed in 2017, I believe it was, basically observe this notion of transferability. It basically is if you ask the model a question, it'll give you an answer, and you learn a little bit. And what you can do is you can basically query a model and then use that to figure out where the decision boundaries are. And you take a sample and you move in one feature dimension until it changes. Now you're on a decision boundary. Then you pick a second dimension, and then you can move all around that particular decision boundary, and you can recover the model. So what's the use of that? Well, you get a bunch of pairs, and you can train this set of pairs and generate a surrogate model. And it turns out that, hey, that surrogate model is also vulnerable. So this is sort of the basic, the standard transferability black box attack. It turns out that this is extremely powerful because now I know that if I can talk to a model, I can attack it. The early days, we thought, hey, you really need to know about the architecture and the meta-parameters and the training data and all of that to attack a model. Turns out you need to know almost nothing. And even to the point where you don't even have to use the same kind of machine learning in order to attack a system. And so we've actually been able to show that particularly if you have high capacity kinds of learning systems and complex architectures, you can learn a lot with these surrogate models. You can train very accurate surrogate models. Things like linear regressions don't literally have the information capacity to capture complex decision spaces, and so obviously it's not quite as effective. But the point is that these are real. So this data is really old. This goes back to the original paper, but it basically said that for the existing systems that were around 2018, the best-in-class learning systems, we were able to just completely fool them, create adversarial samples. But there are larger consequences here. The larger consequences is that not only can I attack a model, but I can actually learn a lot about a service if I observe it. And this is sort of a known fact of security, that reconnaissance is a real enemy if you're depending on the adversary not knowing it. There's also a lot of intellectual property. So one of the really interesting questions is how much of the data of a model can you extract? You can think of membership attacks and friends are all different ways of really just extracting either the training data or the underlying distribution of the training data, which in many cases is sufficient for most adversarial needs. What are we going to do about that? If this is one of our key mechanisms, and the intellectual property that we're generating in, say, our company or our enterprise can be simply extracted by the adversary, how do we deal with that? And there's sort of an existential problem that is, if a model works right, it will give you information. And so there's a whole field that really needs to evolve to really understand that. And areas like differential privacy are actually doing a pretty good job at getting a good jump at making some progress there. And then obviously, if your data is going into a model and the model's giving up something about your data, there's some pretty heavy privacy concerns. I think one of the one things that I would, when I talk broadly about these topics, that we don't talk enough about is simply data curation. And that is, what data are we using to create the model? And then there's sort of the obvious problems like data poisoning, like how do I know that my data, how do I prevent an adversary from inserting, false distributions into our model? But there are other problems as well. How do I know that my data is representative? How many kittens and puppies do I need to show before I know I'm not going to be, say, vulnerable? And then, of course, the reality is that most things that are complex phenomenons are non-stationary. That means they change over time, particularly when humans are involved. If you look at something like, popularity of music on Spotify, that literally changes week by week. And so there's a whole science of how we actually curate data, how we bring data into a model, how do we verify whether it's good, and then how do we retire it from a model over time. And that science is really kind of lagging behind the rest of the ML community. Fairness is a big problem. In particular, models are only as fair as the data that you trained them with, modulo, fairness techniques. If you train a model on things like who gets a loan in Chicago, you're going to disenfranchise some large portion of the community, in particular minorities. And so we have to be really cognizant of how do we actually as a society, how do we decide what the norms are about how we measure and enforce privacy, fairness? Because in the absence of it, we're going to make inequities worse, not better. So let me finish by talking about this gentleman here. So this is Charles Goodhart. He is a very famous economist. Was a British economist, and in 1975 he came up with something that's called Goodhart's law, and it says when a measure becomes a target, it ceases to be a good measure. So the way to think about that statement is to think about miles per gallon in automotives. So miles per gallon is a measure we use here in the United States and variants of it around the world. And it's literally on the sticker that's on the window when you go to buy the car. Now, it was developed in 1975 because there was tremendous concern about the environment. Cars were very dirty at that point. There was lots of leaded gas. The cars themselves were very messy, very to manufacture. And so they had tremendous environmental impact. And society decided, hey, we have to do something about these cars. And so what they said, well, miles per gallon will reduce the amount of gas that gets consumed, and therefore it reduced the lead in the air. And that's great. And so we've been living with that reality, miles per gallon, for nearly 50 years now. But the problem of miles per gallon is that if that becomes the target, the entire industry, automotive industry, is focused on making cars that have low miles per gallon. They ignore everything else. They ignore batteries are incredibly destructive to the environment. Rubber tires are terrible. As you drive down, the tires are literally disintegrating as you drive your car. And that's actually pollution you're putting all over the planet. And so all of the other costs are ignored by the auto industry, more or less, in deference to meeting this miles per gallon. And it's coming back to Charles Goodhart. He said, well, that's the problem. If you create a goal and it's singular and it's focused, it ceases to be a good measure because everybody's going to ignore everything else and focus on that. And I would say that there's a corollary with machine learning, and that is that we are going to get caught up as we introduce machine learning into making societal decisions. People will be focused on making the model happy. And I'll give you an example. Harvard University has a tremendous problem about admissions. It's a very exclusive university, of course. They've historically, certain parts of the population, particularly Asians, have not had as much success getting in, even though they've had, at least on paper, stronger applications. And one of the questions that has come up at Harvard is, hey, why don't we just hand this off to a model? Unfortunately, the problem will be if you hand it off to a model, either you're going to just use old Harvard data and just reproduce the same biases, and the model will just produce it rather than an admissions committee. But the other problem is that people will figure out, there'll be a whole industry figuring out what makes Harvard's model happy. And it'll be something like varsity tennis, because varsity tennis is something that is in predominantly white, predominantly wealthy, predominantly Northeast high schools. Same for California as well. But that will become really important because the correlation between playing varsity tennis will become stronger because of the association between those people who go to Harvard. Because they have all of the other systemic advantages of their environment, they also tend to play tennis. And so that value of playing varsity tennis will be completely will be completely out of proportion. And in a sense, everyone will be generating applications to Harvard, which are adversarial samples. What do I need to do? What are the 3 things I need to do to make Harvard happy? And there's sort of an example of this today on college admissions where people are doing extracurricular activities that they have no interest in, that are generating, they're doing foreign travel and missions and things like that, which really turn out to be paid vacations. But on paper, it looks like outreach. And in that sense, they're sort of creating adversarial samples for applications today. But this isn't just going to be about applications. It's going to be across our entire society. If we decide who gets a loan or who gets a job, the more we do that, the more people will focus on the wrong thing. So the other major problem that I've spent the last half a decade thinking about and writing about, mostly in the public policy space, is we are rapidly approaching a universe in which objective reality is in question. That is, we can create artifacts of pretty much any, we all live in a digital world now. The IRL world is secondary to the digital world in most of our lives. And so we can create an environment in which everything we see around us is fake. And we're seeing more and more of this. We saw this certainly in the election of 2020, and I should cross out 2020, 24. I was working nationally with the elections, and there was a tremendous amount of fake information, tremendous amount of AI generating false information through things like bots and really undermining a public discourse and basic fairness. And so we have a problem in society. We have a problem as a species. How are we going to live in this world? We don't have any norms. We are generating AI faster than we can really contemplate what the long-term effects are going to be. And then, of course, we have to figure out how we can separate the real from the fake, the AI generated from the non-AI generated. And of course, we've been fighting this, Turing test or a reverse Turing test or however you want to think about it. How are we going to address things in the future? How are we going to address this new sort of content? And the reality is that we don't really have any good answers right now. And organizations like Action AI are going to be critical components to that ongoing conversation. I would say, not to be too dramatic, but this perhaps is the single biggest challenge, I believe, facing computer science over the next 25 years. How do we develop systems which will defend our society and ourselves from the misuse of this technology, because it's reached a point that it can do incredible damage. And maybe as a last, perhaps dark commentary. So I was asked some years ago, like, okay, so what's your worst case scenario? And of course, I don't want to, get into sort of broad societal, but I was sort of thinking narrowly about this. And my kids are in high school, and then high school is a horrible place. Kids are in what's called a pre-consequence phase of development. That is, they haven't really learned to understand the consequences of their own behavior, particularly as it relates to other people, and this leads to really negative behavior. But what my worst case scenario is, you take, say, an at-risk 14-year-old girl who's already feeling concerned and has confidence problems, and she gets in a bullying situation. She's getting bullied, and for one reason or another, someone that's bullying her downloads a bot that targets her online and harasses her and generates fake photos of her and makes up stories about her and is smart enough to connect to different parts of her social fabric, either direct or indirect, and people in her high school. And this bot goes and goes and goes and goes. And it continues until she kills herself. What are we going to do? Now think about it. Somebody can write that program probably next week and put it on a website. And some 13-year-old whose pre-consequence development phase can create 1 billion of those in 10 seconds. What are we going to do as a society? How are we going to combat that? How can we avoid that kind of damage? And I think that's our charge. We opened Pandora's box. AI has tremendous positive, will have tremendously positive consequences on us as a society and a people. But unless we learn to use it wisely, we're going to be damaging our society and people will suffer. So that leads us to where we're at. Well, AI is moving faster than we can understand it. And we are beginning to understand sort of at a technical level what its vulnerabilities are, and we're beginning to get our hands around what are the different models, what are the different threat models, the ways to think about threats against these systems. There are a number of things that we have to develop. I mentioned curation and things like that. But not all is lost. I feel like, at least with respect to things like adversarial machine learning, we know how to build safe, secure system out of unsafe, insecure components. It's called engineering. We know using multiple things like multiple models, like an ensemble, of course, that has limited effectiveness against certain kinds of adversarial attacks, but using architectural structures to validate what the model is telling us. And then in the case where the model's telling us something where we may or may not believe it, but the consequences of acting on that information could be dire, then maybe we have to move to other kinds of systems. It may involve humans, and it may involve some closed form. But building systems that integrate AI and make the system secure is our hope is our hope for the future. At least my vision of hope for the future. We will never make machine learning invulnerable to adversarial samples. That's just by definition, that capability will be there. We need to build the systems that will actually be able to defend against them. So what do we do next? You guys are doing it. So I probably don't need to go too far down this rabbit hole, and I'm out of time. I think there's a couple of things that I would just remind you is that computer science, I mean, I think we've been extremely effective at building a community. And again, your institute is another great example of a real kind of national, international scale efforts in this space. I encourage people to think laterally. We need more computer sciences talking about things like public policy. We need to be evangelists for the safe use of AI, and then get involved. And so with that, I will stop there and take questions. Oh, wait, a couple of things. Sorry. If you're interested, 2017 or 2019, I and a guy named John Launchberry and a lot of other people, and I think Giovanni, you were involved in this. We had about 150 people contribute to the national strategy that asked two questions. How can AI be used to improve our security profile? And then how do we secure AI? And so this sort of it's a high level document. They're still using it for things like budgeting for the US government. But it gives you a good sense of, at least, maybe perhaps a little bit dated at this point, a good sense of the space of opportunities. And then finally, a big thank you to National Science Foundation. I've been running the Center for Trustworthy Machine Learning, which is a frontier project. It says 5-year. We're on year 7. We're continuing to chug along with I would argue great success. So finally, I'll just say thanks and welcome questions. And then if you have questions, and I don't know why this has an old email on it.
Noticing that.
Yeah, I haven't seen that email in 2 years. So ignore that email. Go to patrickmcdaniel.org. With that, I'll just stop there.
Virtual clap. Thank you. Shinan, you're in charge, so I'll let you lead.
Sure. Yeah. Thank you, Professor McDaniel. This is such a very visionary, insightful talk. I learned a lot. And we have one question in the QA section. And please feel free to ask more questions like our audiences. So actually, for me, myself, I have a question. Basically, I love, right. Yeah, I love the fact that you mentioned like adversarial examples being a nature of machine learning. It's agnostic to the model itself. Now we are kind of stepping to the age of super large models, large language models, like large vision models. What do you think these adversarial examples might evolve in this age? Or do you think there are like some more opportunities for attacks or defense in this age?
Yeah, so so this is a great question, because I feel like I want to add a little bit to this talk, because there's the first thing we have to accept when we're talking about large language models is that we have no hope of reasoning about them. We simply, as a practical scientific exogen, we have no ability to reason about 1 trillion inputs. So understanding that we are going to have, and perhaps that's a bit of an overstatement, but hopefully you'll get the sense of what I'm getting at. So understanding the complexity of the beast is that if we're putting our energy into something right now in that space, we got to look at what goes into that thing, and we got to look at what comes out of it. I think rather than trying to understand what the samples, the adversarial samples in that space are, I think we have a lot more profit to be made about, okay, we understand this thing is magic, and it's an incredible beast that is fundamentally altering society. But what can we do when we use it within the context of a system? How can we rationalize the input? Can we look at the input? What are we asking it to do? And then we see a lot of this on like jailbreak attacks and things like that, which is sort of like the first generation of these things, where we look at the input and we look at the output. Actually, I'm getting ready to publish a piece of work that's looking at LLMs. Basically, I'm trying to extract the harmfulness classifier out of some of these models. Basically, and we know that there's a classifier embedded in all of these things that have been aligned. I'm trying to extract, after it's been aligned, trying to extract the classifier so that I can look at it in isolation, and then we can do some more rigorous testing of this sort of classifier. So that's one of those examples where, okay, we know there's a classifier in there. The output is going to be a result in part of this classifier. Can I extract that classifier? Can I reason about that? Can I harden that classifier and then maybe reinsert it? I don't know how that's going to work, but that's perhaps down the road. But those are the sorts of things I see us having success in the near term. So I think the larger question is, we have to be very cognizant of how we use these things. I think the early examples that everybody laughs about how like it was hallucinating case law for these lawyers, which is sort of funny, but at the same time, in the wrong context. What if it was hallucinating diagnosis, right? If you're using this in a medical context, and sometimes those diagnoses can be very, very difficult and very subtle. You do not know. And so we have to be very cognizant about, are we using this in a context that is going to be, it's going to be safe? And we have to know that it could be wrong, and it could be generating things that are either incorrect or harmful. And we have to be really conscious. And this is like an ethical discussion, like, what ethically can we trust coming out of an LLM in what context? And I think that's a broader question.
Thank you. And how about the last question being like the one question from the audience? So basically, Matthew is asking about like the practicality of these attacks being carried in, for example, image recognition systems that actually causes real world impact. Yeah, it's a harsh question. Like, does it mainly live in academia or the bureau data? Or if it's not that practical, what do you think are the next steps to make it really practical?
So first of all, these attacks are real. Yeah, things like adversarial patches, the way to think about this trade-off, when I did the saliency versus the overlay, which is really just about how many features and how much you actually want to change things. Attacks come on a spectrum, right? They're not, a lot of attacks sort of happen in the middle. The more you're willing to perturb the input, for example, if you think about the stop sign, that's brilliant work that they did. I think it was Columbia and some other folks, where they had the patch, right? That's obvious. We can see that. But in context, I'm driving down the road. I'm paying attention to the road. I'm not looking at that stop sign, right? If the adversary knows you're not going to be paying attention, or they can make that sample really hard to sort of, it's not eye-catching, then, they can sort of hide the existence of it. But maybe what I'm trying to say, if you're willing to perturb the environment enough, it's real, right? In the case of doing a straight up FSDM attack, you got to be inside the car, because you actually need to be able to change the light intensity of each individual pixel. And so that's a data transformation, but that's a real attack. right? So all you got to do is subvert a controller inside. I mean, it's all in one giant data bus. Every automotive system is just like one big network anymore. As long as you compromise something on that network, then all you have to do is insert yourself between the sensor and the model. And anywhere in that data pipeline that you can insert yourself, you can actually do that kind of transformation. So it's really just a question of what are the threats that you're willing to take. So I think absolutely they're real. And you will, the reality is that those of us that have been in this business for a long time, if there's money to be made, they'll find a way to make the attack work.
Absolutely.
Thank you so much, Professor McDaniel. This is such amazing sharing, and we learned a lot. And thank you to the audience as well. Thanks for all of you being here. And yeah, I think maybe it's time.
Yes, as the
Johnny.
As a colleague, director, fan, thank you, Patrick. This was amazing. And, I really hope I'll see you at the end of June and join us for our Action Institute Day so that we can hear more about your research. And we can share our research with you so you can see more details what we're doing at the Action Institute. Some of the stuff includes some work on adversarial machine learning, but it's focus also on using AI for various cybersecurity tasks. So I'm looking forward to having you in Santa Barbara and have a in-person discussion. So until
100%.
then, have a fantastic holiday season.
Thanks so much. This was a lot of fun. Appreciate it.
Awesome. Thank you. Oh,